Greetings from the Hermitage, and welcome to the fifth video in our series on one-step addition subtraction equations. Let's do a little review where we write equivalent expressions, equivalent equations for this equation with just numbers. So we have the numbers 2, 5, and 7, and we want to have three equations that are equivalent or true statements of relationship between those two numbers. I've given you the first one. We know that 2 add 5 equals 7. We can also write that 2 equals 7 subtract 5. And we could also write 5 equals 7 subtract 2. All of these three equations are true statements, so they are equivalent expressions of the same relationship. Now let's move on to a situation where we have numbers in one case and just letters in another, and we'll do exactly the same thing. We'll start with the numbers. We have 2 plus 5 equals 7, and we have A plus B equals C. And we'll write 2 equals 7 subtract 5. We'll go ahead and lock down the A, and we can write A equals C minus B. That mirrors this expression with the numbers. And then once again, we can write 5 equals 7 subtract 2. In this case, we'd lock down to B, and would have B equals C minus A. And the point being that whenever we rewrite these equations, something that was on the left-hand side of the equal sign changes sign whenever it moves over to the right-hand side. And it's the same thing with the letters. Now, in this situation, we're going to have this original equation that we've been using, and this time we're going to mix letters and numbers. So we'll follow through. The first thing I'm going to do is write 2 equals 7 subtract 5, following the same pattern. Over here on this side, we'd have x equals 7 subtract 5. Once again, over here, we would have 5 equals 7 subtract 2. And once again, over here on the right-hand side, we would write 5 equals 7 subtract x. Typically, whenever we have an equation like this where we have a letter and a number equals another number, what we're wanting to know is what value of the letter makes that a true statement. And the way that we determine that is to rewrite that equation so that we isolate the value of x. We have x equals 7 subtract 5. Following the same pattern that we had over here and in the previous slides, whenever a number on the left-hand side of the equal sign, whenever we rewrite an equivalent expression, if it shows up on the right-hand side, it changes the sign. And that's what we saw right here. And from this, we have x equals 7 subtract 5, and we know that's 2. And that's that 2 right there. Now, whenever we have these simple equations like this, these one-step addition subtraction equations, it's easy to visualize these things as simply moving a number from the left-hand side of the equation to the right-hand side of the equation and writing an equivalent expression. The difficulty comes a little bit later on whenever the equations aren't so simple anymore, and that's when we need to have a more formal way of doing things. And to do that, we have a set of rules called the properties of the real number system, and there's a video on my channel that talks about that, but we're going to introduce one of those now that's used very specifically for these types of equations where we have a letter plus or minus a number equals another number. And that property is called the additive inverse. The great thing about the additive inverse is that whenever we apply that property to an equation, we get a 0. So a plus the opposite of a equals 0. I can put in any number I want, so let's say 7 plus a negative 7 equals 0. We could say, now look, this a is the opposite of this a. So if I had negative 13 and I want to zero that out, I'm going to add the opposite of a negative 13, which is a positive 13, and that equals 0. Notice that we don't write like 7 subtract 7 equals 0. Subtraction is defined as adding the opposite. Subtraction, hope I can spell that right. Subtraction means add the opposite. Subtraction means add the opposite. We'll try to keep that throughout the year whenever we're doing these types of equations. If I forget and I say subtract, remind me so that we're consistent the whole year. All right, here we go. We've done this problem already, and all we did was write an equivalent expression. We did this. We said x equals 7 subtract 5. And that was an equivalent expression of this, right? Remove the 5 to the right-hand side, and it changed the sign from a positive to a negative. But now let's do it formally. We'll start developing these formal solutions now so that whenever things get more complicated a bit later on, we have a good handle on how to use them. So whenever we have x plus 5 equals 7, we want to solve this equation for x. That means we want to get x all by itself. We want to isolate x. And to demonstrate that I want to isolate that letter, I double underline it. This is what I do. You're not required to do that, but it helps. And now I need to zero out that 5. So we would write x, add 5, that's the original equation we have, and to zero out that 5, we're going to add the opposite. And we have to do exactly the same thing on the right-hand side of the equal sign. So we're going to add that negative 5 over here. You recognize this as the additive inverse. Now we have x equals, and x is isolated now. It's all by itself. 7 can be written as 2 plus 5. And here we have that negative 5 again. Once again, this is the additive inverse, and we know that that becomes a 0. So at the end of the day, we would have x equals 2, and we would box that in to demonstrate that that's our answer. The additive inverse also works whenever you have a negative number with the variable, with the letter. Once again, we want to isolate that x. I'm going to lock him down, take care of everything else first, and then come back to that x. We need to zero out this negative 6 to get that x all by himself. So we have x, negative 6. We're going to add the opposite. The opposite of negative 6 is positive 6. 12 on the right-hand side of the equal sign. We added a positive 6 over here, so we have to add a positive 6 on the right-hand side. You recognize this as the additive inverse. That's a 0. So we have x plus 0 equals 12 plus 6 is going to be 18. We know that you add 0 to anything, you get the same number back. That's called, in this case, the additive identity. When we get the same number back, it's an identity. So we have x equals 18. Now the question becomes, what if that negative sign is on the letter instead of on the number? We have a couple of ways of handling this situation. I personally prefer to get rid of that negative sign on the x term, and the way we do that, we want to zero him out. So we have negative x, add the opposite, plus 18 equals 7 plus a positive x. You'll recognize this as the additive inverse. It works with letters, it works with numbers. That's going to be 0 plus 18 equals 7. Add x. Now we have the x on the right hand side. It's okay, it doesn't make any difference whether it's on the left hand side or the right hand side. This equal sign works in both directions. Now we need to isolate this x, get him all by himself. That means we have to zero out this 7. To zero out a 7, we'll add the opposite. And since we added negative 7 on the right hand side of the equal sign, we have to add negative 7 on the left-hand side. It's going to be 18 plus a negative 7. You recognize this as the additive inverse. That's a 0. So we have x equals what's left over here. 18 can be written as 11 plus 7. And then we add the opposite. Because it's already there. This cancels out and we have 11 equals x. So let's review for a second. Summarize what we've seen. We introduced something called the additive inverse. And the general expression for that was some number A, any number A, add the opposite, and that equals 0. That comes in very handy whenever we're trying to solve an equation like x plus 14 equals 26, because our goal is to always to get that letter all by himself, and that means that you can't be adding or subtracting anything from it. But if you add a 0, it's still the same thing. So we would have x, employing the additive inverse, we would have that number add its opposite. And we'll do the same thing to the right-hand side to maintain the equality. We're going to add a negative 14. Those cancel out, and now we have x all by itself on one side of the equal sign, and then 26 subtract 14 is the same thing as 12 plus 14 plus a negative 14 just equals 12, because these would cancel out. Have x equals 12. That about wraps it up for the additive inverse and these one-step subtraction addition equations. So at the end of the day, there's only one thing left to say, and that is that's all, folks. Be safe, con cuidado, and thanks for learning.